Okay, we're going to look at section 2.2, number 23, and we're going to use row reduction to show that the determinant of this matrix here, A, B, and C are some constant, some real numbers. The determinant of this matrix is equal to this interesting sort of factored expression. So we're going to use row reduction. It can be shown using other techniques like cofactor expansion or the permutation approach to finding a determinant of 3 by 3 matrix, but we're not going to do that route. We're going to do it with row reduction. It's actually going to be easier to come up with this formula doing that. As we do the row reduction, I'll just have you remember the sort of effects of performing row operations on a matrix, how that affects the determinant of that matrix. And the one that's going to come into play here, one of the ones at any rate, is if B is the matrix, if we have a matrix A that's n by n, and B is the matrix that results when a single row is multiplied by the scalar k, then the determinant of B is k times the determinant of A. Now, what that looks like, and basically the proof of that you can see is here, that if I have the matrix down here, where I have A11, A12, if this is matrix A, if I multiply the first row by k, so I get this matrix here. Okay, here's the A matrix. This would be the B matrix from this up above. Then the determinant of B is k times the determinant of A. And you can basically see why that's the case, because if I do cofactor expansion along the first row, here's what it looks like for this one. That k can be factored out. And what's left then is cofactor expansion along the first row for matrix A. And so it's k times that determinant. Now, here's the tricky thing. When we're doing row reduction, what would we be doing here? Maybe multiplying this first row by the reciprocal 1 over k to get to here. And I'll have you note, when we multiply by the reciprocal 1 over k, the determinant of this matrix is k times the determinant of this matrix. So it's like as if we are factoring out the k from the determinant, if you will. So that's the way this relationship here in theorem 2.2.3 part A is exhibited in the process of row reduction. The others are pretty straightforward. If we interchange two rows, we change the sign. The determinant of the new matrix is -1 times the determinant of the original matrix. And here's the neat thing. If we do any adding a multiple of one row to another, the determinants are the same. They don't change. So that's going to be key in this process. So let's go back and look at this matrix. I've written it out here. And the first thing I'm actually going to do, the thing I'm going to do is basically put it in triangular form, which I'm kind of going to go like I would if I was doing Gaussian elimination. I got a leading one here. I'm going to try and get zeros underneath here. How do I do that? Well, I'm going to take row 2 and add -a times row 1. We'll zero that out to row 2, right? To get a 0 here, I'm going to take -a squared times row 1, right? And add that to row 3 to get a 0 here. And so that's what I've done here. And notice when I do row 2, basically -a times row 1, I get a minus a, b minus 1 times a is a, b minus a, c minus a. And then row 3, I'm going to do row 3 minus a squared times row 1. So a squared minus a squared is 0. B squared minus a squared is b squared minus a squared. C squared minus a squared. So here's this determinant. And since I'm adding a multiple of one row to another, remember what we said, that doesn't affect the determinant. So these determinants are going to be equal. Okay. Now, typically we'd say, okay, we want to get a leading one here and then a 0 beneath here. But I'm not going to get a leading one here because I noticed something. B squared minus a squared, that's a difference of squares. It factors as b plus a times b minus a. And b minus a is right here. Notice if I multiply row 2 right now by b plus a, or really negative the quantity b plus a, then I can get a 0 here. Once I get a 0 here, notice I'll have zeros all down the main diagonal. I'll have a triangular matrix. Remember, the determinant of a triangular matrix is the product of the main diagonal entries. And that's what I want to do. So I'm actually going to multiply or add a multiple of row 3. I'm going to add negative b plus a, negative the quantity b plus a to row 2, add that to row 3. Same thing as to subtract the quantity B plus A times row 2 from row 3 and replace row 3 for that with that result. Okay, so first of all, you got a 0 here, so 0 minus 0 is still 0. Here I got B squared minus A squared minus what? B plus A times B minus A, again, is going to be what? B squared minus A squared. So B squared minus A squared minus B squared minus A squared is 0. That zeroes that out. The question is, what goes here? What goes here? Okay, so this is going to be row 3, which is C squared minus A squared, minus B plus A times row 2 entry in that column is C minus A. So I've written that down here. So it's C squared minus A squared minus B plus A times this quantity, C minus A. That's what goes in this entry. Okay, but I'm going to do some simplification here. First of all, I'm going to FOIL this out. First, B times C is BC, outer is negative AB, inner is positive AC, last times last, positive times negative, negative A times A squared. So that's what that FOILs out to. But now I'm going to simplify. I'm going to distribute this negative sign through this whole thing now, right? So all these signs change: negative BC, positive AB, negative AC, negative A squared. Sorry, minus times minus, positive A squared. Okay, and then I'll note that the negative A squared and the positive A squared, right, those combine to 0. I accidentally made a mistake there, sorry. C squared stays there, it doesn't disappear. C squared minus the BC plus the AB minus the AC. Okay. Keeping in mind where we're trying to get to, I mean, don't lose sight of that. We're trying to get an expression for this determinant that was sort of factored form. So it makes sense for me to think about, can I now factor this expression? And I can. There's no common factor for all 4, but I can do grouping. Try that. C is common to the first 2, so factor that out, leaving a C minus B. And then an A is common to both. I could pull that out, leaving a B minus C. But in order to factor, I have to have left the same factor. And is it the same factor, C minus B, B minus C? No, they're not the same, but they are obviously related, right? One is just what? Negative 1 times the other. So in fact, instead of factoring out a positive A, if I factor out a negative A, I'll be left with negative B plus C. Negative B plus C is the same as C minus B. And so that's what I need to do. Now I've got the C minus B, factor that out of both. What's left? C minus A. So C minus B times C minus A, that is what goes in that lower right entry. So quite a little bit of algebra to do there, right? C minus B times C minus A. Well, now we're essentially done, because now what's the determinant of this matrix? Notice it's a triangular, upper triangular matrix. Everything below the main diagonal is 0. For any triangular matrix, the determinant is equal to the product of the main diagonal entries. And so this is going to be equal to B minus A, 1 times B minus A times C minus B times C minus A. And that is the expression we were supposed to show. And we have done it. So I hope this helps on number 23 in section 2.2.